This is lecture 20, and lecture 20 we're going to talk about bagging and random forests. So last lecture we had looked at trees. And in particular, we had looked at what are called carts, which stands for classification and regression trees. And carts or classification and regression trees are a particular instantiation of decision trees that are very popular in the statistical community. So typically when people talk about decision trees, they're talking about carts in particular. And I just wanted to tie up a couple loose ends on the carts, and then we can start talking about how we can, some problems with them and how we can solve some problems with them. So the first thing I want to talk about is categorical variables. So if I have a categorical variable, so let's say consider a Q level categorical variable, a split here. So we talked about splitting variables, but they kind of split for a categorical variable is really just putting some of the categories in one group and some of the categories in another group, right? There is no kind of particular geometric way to view it because these are unordered categories. And a split is just dividing the categories into two groups. So maybe I have my categorical variable that has levels 1, 2, 3, all the way up to level Q, and I'm going to split here this thing, and so maybe I put levels 2, 3, and 5 in one category and 1, 7, and all the way up to, I don't know, Q in another category. So you just divide the categories into two groups. And that's basically a categorical, a split for categorical variable. Now, the problem here, or a problem that we can run into, is that if I have Q levels, then I have how many possible ways to do this division. And you can do the counting in this 2 to the Q minus 1 possible quote splits of this categorical variable. And so if I have a categorical variable with a huge number or a large number of categories, where Q is large, then this becomes a problem because I have a lot of different splits I would have to search over for a large value of Q. It turns out there is a kind of nice solution to this in most cases, or in many cases. So if y are the variable we're trying to predict with our tree is numeric, that is, we have a regression problem. So we're fitting a regression tree to this. I can order all of my levels. So let's say all of my Q levels by the mean, let's say their mean value of y among observations. That is, we're going to take this variable that we're trying to split on, and we're going to, for each of the q levels, we're going to look at which observations have what level, and we're going to calculate the mean y for each of those different possible levels. So let's just leave it like that. And so what I can do is I could put these out on a line. So maybe if I put out this maybe is the y bar for group 1. This is the y bar among observations for level 3. This is the y bar over here on my number line for observations where the level is 5, and this is maybe 4 is really far over here. So 4 have things that have this the category 4 will have a really large y bar. All right, so you can put these all in a number line, and then we could basically just split this as if it's numeric. So, maybe I make my split here. Maybe this is the best place to split things. And so if I split here, this would basically correspond to a split where the levels 1 and 3 go into one box, and the levels 5 and 4 go into the other box, right? So this would be an example of a split of my categories. So all I would do is I would calculate y bar according, kind of group wise, according to the levels of this variable. There'll be q levels, so you'll have q y bars. You arrange them on the number line like this, and then you just treat that as quantitative, and you split as if it were, a quantitative variable. And so it turns out this is the best thing to do. Turns out this finds the optimal split finds the optimal split for my regression tree. So this is a really slick way of finding the optimal split. You can basically kind of do this kind of trick where we treat this thing as numeric in a cute way. You basically arrange them by their mean y values, treat it as numeric, and you make the split as if it were some numeric variable you're splitting, and turns out it's the optimal way to do it for a regression tree. So this is for a regression tree. For a classification tree, so I guess there are two situations. For binary classification, I'll basically say what do we want to say? We can say can do similar as with to the similar procedure to the regression tree, where we order by percentage in class 1 as opposed to class 0. Right? It's a binary classification problem. So you could arrange now my number line, instead of by y bar, you just arrange by the percentage in class 1, and then split it as if it were numeric. This finds the optimal split if my node impurity is either using the Gini index or if I'm using entropy. Let's say for Gini or entropy. Unfortunately, for the multi-class problem, there's no such trick. And so fitting a multi-class if I have a multi-class classification problem with a classification tree and I have a Q level factor, I'm just going to have to try all the different levels. Unfortunately, there are some heuristics people use to try to approximate it, but the only way to be sure you're getting the optimal split would actually be to try all levels. So I think people actually don't do that. What they do is they use some approximation method to try and approximate the best split. But yeah, so factors, so categorical variables can be a little more complicated because, as I said, you have theoretically 2 to the q minus 1 minus 1 possible quote splits, which is just divisions of your levels. But in a regression tree, not so bad, and even in a binary classification tree, there's some actually really slick ways of finding the optimal kind of split, i.e. division of the levels. But in the multi-class problem, there is no way to ensure you get the optimal split, so people have to basically approximate it at the end of the day. The other kind of caveat here is the warning, I'll say, is that trees tend to like to split on categorical variables with many levels. So the fact that there are so many possible potential splits means that these trees tend to like to split on categorical variables, and you can very easily overfit because there are so many possible splits to make, 2 to the q minus 1 minus 1 possible splits. So the warning here is to be careful. Typically, we don't want to have like a 100-level factor that we're going to include in our tree. It's going to be really easy to overfit if you have that many factors. It's going to just have too many options for that kind of categorical data, categorical variable that we include. So let me just say easy to overfit. Careful. So we tend not to want to include categorical variables with a ton of levels. And my last, so let's just see what we say here. We just want to talk a little bit about categorical variables, and that's the main points about categorical variables. It can be a little complicated for multi-class, but and just to think about what does a split mean for a categorical, because you can't do the geometric interpretation, just basically dividing up the classes, the options for the categories. And the second thing I want to say, and I'll keep this kind of short, is for missing data, is that one of the nice things about trees is that they can handle missing data pretty easily. In fact, natively, many of these methods, we haven't really talked about missing data. It's a whole huge topic in and of itself. Many of these other methods, we assume we have complete data. I can't have a matrix with missing values in it. And so, when I fit a regression, how do I handle missing values? This is this whole big conversation. For trees, we can actually very kind of nicely handle this. So again, for categorical variables, if we want to handle missing data, all we do is add a quote missing category. So that's actually really easy. And that can make sense to do as long as you're missing this. Things are kind of missing in the same way. Categorical variables, let's just add on a category of missing, and then our trees can just, if you're missing data, well, we're going to say, and you're missing. And we can do prediction off that. For numeric, actually the missing data is a little bit harder. Basically what we do is we try to keep track of, and this is a pretty large procedure, but I'll just describe at a high level what's going on. Keep track of, quote, surrogate splits, which is basically splits using other variables that give similar divisions. So if I were to split on x1, and that would divide my data into these two groups, I could potentially split on x5, and it would give a similar kind of division of the two groups. And so the idea here is if I have missing data in one variable, use a surrogate split on another from another variable if I'm missing, let's say, missing values for 1. So I'm missing, if I get to a point in my tree and I have to go either left or right, depending on what the value of x is, or what the value of x1 is, but I'm missing x1, what should I do? Well, if I have in the back pocket a surrogate split, if I split on x5, that will be similar. Well, and I'm not missing x5, I can just split on x5 instead, and I can replace that in my tree. So that is our kind of tops off our last little tidbits on classification and regression trees. What I want to say now is that a problem with classification and regression trees is that they tend to have really high variance but low bias. i.e., it's easy to overfit. We could just grow a really, really, really large tree. I just keep splitting all the way down until I have one observation in each of my leaf nodes. I just have one rectangle around each of my observations. It's like, it's really easy to accidentally overfit. Now you wouldn't, it'd be like fitting a k and n regression with k is equal to 1. It'd be really easy to do that. And so one of the issues that people have with carts is that they tend to be really overfit, so they have a low bias, they can really complicated shapes, but they have this high variance. And one of the ways that we can solve this is through a technique called bagging, and in particular a particularly great implementation of bagging called random forests, which is going to actually not only not have a problem with the high variance of carts, but is going to use this high variance and low bias to its advantage. So let's talk about bagging. So bagging is a kind of meta method. We're going to do a real quick recap of the sample average. So X bar is our kind of typical sample average, right? So if the real quick review of mathematical statistics is that if I have some xi and they are from some distribution, I guess I maybe should call these x sub n's. So these are my observations. These are like the rows of my design matrix rather than the columns. And they all come from some distribution with a mean, let's call it mu, and a variance of this distribution, sigma squared. And we consider, among my observations, looking at x bar, which is my arithmetic mean, which is maybe 1 over n times the sum of my xn's, right? That's a typical definition of the arithmetic mean. We have some properties of x bar. One of them is that if I look at the expected value of x bar, right? So here we know that the expected value of any of my individual samples, x ben, is mu. By definition, we said the mean is mu. And we know that the variance of any of my x bens is sigma squared, right? By definition, that's the variance. If we look at the arithmetic mean, so we combine these together, the expected value of x bar is, of course, the expected value of 1 over n times the sum of that. I can pull out not only the 1 over n, because that's a constant, but I can pull out the sum because expectation is a linear operator. So I can push it through sums and constants, multiplicative constants. And so I get 1 over n, the sum of expected values, which of course is 1 over n. All of my expected values are mu, so this is just 1 over n times n mu, which is mu. So it turns out that the expected value of x bar is the same thing as the expected value of any of my individual x of n. So x bar, taking the arithmetic average of a bunch of identically distributed random variables, doesn't change the mean, right? The mean doesn't change. If the average of these x of n's, if on average they're mu, when if the expectation of the x of n is mu, then if I average them, I'll also have the expectation be mu. So that's property 1 of arithmetic means. Property 2 is that if I look at the variance of x bar, this is the variance of 1 over n sum of my x of n's. And I can pull out of my variance, I can pull out constants, but I have to square them. So that would be 1 over n squared times the variance of the x of n's, or sum of the x of n's. Now there's a formula for the variance of the sum of a bunch of variables is the sum of the variances but I can't generally just push that variance through. I have to account for the covariances. How do I want to write this? Let's say n not equal to n prime. I have to add on the covariances between all pairs. So if I have pairs n and n prime, if I have to include the covariance between each, kind of pairwise between each of these. So that's my formula. Now, there are a couple special cases of this. If all of these things have the same covariance, so the covariance between any n and n prime, let's call it, well, let's say the correlation between n and n prime, let's call that rho, and that is the same thing as saying that the covariance between n and n prime is sigma squared times rho, because they all have the same variance of sigma squared, and so the covariance, the correlation is the covariance divided by divided by, well, the square root of the product of the variances, which in this case is going to give us sigma squared. That'll be the square root of sigma to the fourth. In this case, if they all kind of, if we, let's say, idealize things, say they're all correlated equally with each other, 1 over n squared, I'm going to get n sigma squares, right? Because each of these things is sigma squared. Each of these things is sigma squared rho. So we'll get n sigma squared plus, and how many of these am I going to get? I suppose it should be n times n minus 1 sigma squared rho, right? How many pairs are there going to be? N ways to choose the first one and n minus 1 to choose the second one, right? So that's how many things will be in the second sum. Each of the things in the sum are sigma squared rho. So this is what I'll get, and I'll get at the end of the day sigma squared over n plus n minus 1 sigma squared times rho. So I suppose another way you could write this is you could distribute that n minus 1 through, oops, I'm sorry, this should be n minus 1 over n, right? There we go. How could I distribute that through? Well, this would be sigma squared over n plus sigma squared rho minus sigma squared over n rho, which gives me what? It should be rho sigma squared, the middle term, plus sigma squared over n times 1 minus rho. Okay. So there are a couple different ways to write this, either this top way here or this bottom way here. So either of these are kind of equivalent. Okay. Now, this isn't a lesson on mathematical statistics, but we'll get to the point real quick. So basically, if I average things, the mean stays the same. The variance is going to depend on the correlation. If, and we're going to get this kind of formula, well, let's just use the second one here. It's going to be rho sigma squared plus sigma squared over n times 1 minus rho. If rho is 0, then the variance of x bar is going to be what? It's just going to be sigma squared over n. Now that might be a formula you're more familiar with. So that's a cute little fact. So let's just put that in the back of our mind. So basically, if I can, so what do we need for this to be true? We need their correlation to be basically 0. And if that's true, then if I average things, I'm not going to change the expected value of these things. But if I can average them, and I can average uncorrelated things, I'm going to reduce the variance. So the variance of any of them individually was sigma squared, but if I average together n of them, I reduce the variance of them. So this is why we like averages, right? Because they don't affect the mean value, but they reduce the variance. So why are we talking about this? If we go back to our problem with carts, which is that they have a high variance, but a low bias, we might be able to fix this. Instead of averaging together numbers, we might be able to average together methods. So this is basically called an ensemble learning method. And this method is called bagging. and this is an ensemble method, which means we're going to be combining in an ensemble together multiple learning methods. So the idea with bagging is that, let me just write out the algorithm. Step 1 is I'm going to draw some number b, which is called bb for bagging, samples with replacement from my training data. And how many samples we draw, so these are going to be pairs of not only the x's, but the y's. So they're going to be pairs of x and y, and we're going to grab we're going to sample with replacement kind of training pairs from my training data. But we're going to draw not just one sample, we're going to draw b samples. So S1 is going to be a sample of some number of training data points. S2 is another collection of samples of training points. S3 is another collection of training points, all the way up to SB, which is our final collection. So each of these, let's just say for the sake of argument, they're each going to be size n. So I'm going to draw this with replacement. And so we may get some replacement, but that's okay. I'm just going to draw a bunch of samples. I'm going to draw a random with replacement sample of my training data points, call that S1. Draw another random sample of my training data points, call that S2. Another random sample of my training points, S3, etc. I'm going to do this some capital B times, and B is going to be potentially a large number. Our second step is we're going to train a method on each sample. Let's call it S little b. And let's call this f hat b. So on SB, on the bth sample, we're going to train a method. So take a collection of our training x's and training y's. We fit a method on that random sample with replacement. And we're going to call that method f hat b. And we're going to do this over our capital B methods. So little b goes 1 to capital B. And then, I went 1, 3. This should surely be step 2. And step 3 is then we're going to combine the methods that we've learned on each of our subsamples. So step 1 is draw some number of subsamples, each of size n. On each of these subsamples, we'll train a method. So now instead of having one classifier, I have some capital B classifiers. And then step 3 is I'm going to combine the FBs. Now for a regression context, what I'm going to do is I'm going to say that f hat, the final classifier, let's say this is going to be called a bagged method. Let's call it f hat. So we're going to combine the individual classifiers learned on the random subsamples. We're going to combine them together to make what's called a bagged method. We'll call the bagged method f hat. And the way we're going to combine them is that for a regression context, we're just going to straight up say f hat predicting at some value little x is just going to be the average value of the predicted value for each of my constituent classifiers. For a classification context, I'm going to say the predicted class at X is going to be the class with, how do I want to say this? Let's say the plurality class among all of my predicted subsample classifiers. So basically what I'm going to do is I'm going to predict F1 hat, F2 hat, all the way up to F capital B hat at X. Now each of these are some class. Maybe the first one is class 1, the second one predicts class 2, the third one predicts class 1, the fourth one predicts class 1, right? And I'm going to say all of these get a vote. So this is basically, sometimes this is described as majority vote among my FB hats. All of them get a vote. So one of them votes for class 1, one of them votes for class 2, the other one votes for class 1, right? And whoever wins the vote among all my subsample classifiers, that's what I'm going to predict. So in either case, we're basically kind of getting a consensus view. So a bagged classifier, what it's doing is that it's going to subsample my data a bunch of times, take a bunch of subsamples, and then it is going to train a method on each of the subsamples of my training data. And the ultimate prediction is going to be a consensus prediction. For regression, it's going to average together the prediction among all my subclassifiers, my subsample classifiers. And for classification, I'm going to take a majority vote. I'm going to let all my subclassifiers vote, and whichever one wins the vote, whatever class wins the vote, that's what I'm going to predict. So it's actually a pretty simple method. But it's a fairly powerful method. So why is this a good idea? And why was I talking about X bar? Let's say, why does this work? Or why does this help? Why is this a good idea? Let's first talk about regression. That's the far easier case. We know that, so for regression, our bagged classifier is just the average answer among all of our subclassifiers, or subsample classifiers, right? And we talked about what happens when we average things together. It doesn't change the mean, but if we have things that are uncorrelated, it's going to reduce the variance, right? So if we go back to our discussion about MSE, for regression, MSE of some classifier F hat, from some regression method F hat, is the bias of F hat squared plus the variance of F hat, right? And so let's look at each of these constituents. One, the bias of F hat is the expected, so let's say the bias of F hat at some value X is the expected value of F of X minus the true value. So what's the truth? And what an expectation is this thing going to predict? And for a bagged estimator, what we get here is that this is the expected value of our average of our subclassifiers, subsample classifiers, minus the truth. And we know that this is going to be, from our discussion about X bar, so this thing is basically X bar, but instead of X's, we have F's. And so this thing is just going to be the same thing as the expected value of any of our individual Fi. And so this is the bias of any of our individual ones. So what I've shown here is that the bias is unchanged. That is, the bias of our bad classifier, f hat, is the same thing as the bias as any of its individual constituents. So bagging doesn't change the bias. What about the variance, where our MSE is the bias squared plus the variance? So far, bagging does nothing for us. Doesn't change the bias. If we want to produce a method that reduces the MSE, we either have to reduce bias or reduce variance. Bagging does not change the bias. However, the variance of our bag classifier, we said this is going to be the variance of basically x bar, but instead of x we have f's. So it looks something like that. And we said that this was equal to, if we go back up to x bar, we did this whole calculation, that if we assume that these things are kind of equally correlated with each other, this is rho sigma squared plus sigma squared over n times 1 minus rho. Something like that. Where we're assuming that the correlation between say fi, I guess I shouldn't use I, should I? It should be b, right? fb. I don't know why I switched to I here. It should be fb. Fb and fb prime is rho. So they're correlated, and the correlation is rho. And the variance of any of these things, I guess they had hats on them too, is sigma squared. Then we potentially can make this thing smaller if we're careful. If we can choose f hats so that rho is close to 0, then the variance of my bagged classifier, f hat, is, let's say, basically sigma squared over n, which is the variance of any of them individually over n. And so what we have done here is we have reduced the variance over the individual classifier would have some variance, and we have our classifier overall has reduced, the bag classifier reduces it by an order of, whoops, this should not be b, should it be? Should not be n, right? It should be b. If I have b things in my classifier, this would be b, right? Now, it assumes that I can choose some rho approximately, some way to build these so that they're uncorrelated. And that is basically why we're doing this whole subsampling thing. We're doing the subsampling thing. Hopefully, when we do this and we build them, if we do it correctly, we'll get rho that is kind of close to 0. And so we'll have to think about how we're going to build classifiers where that rho is close, approximately equal to 0. And so the idea, of course, MSE, right, is my bias squared plus my variance. And what bagging can do is it leaves this unchanged, leaves unchanged. It leaves the bias unchanged of the method, but it can potentially reduce the variance. And it can reduce the variance if we can figure out a way to build these things, these individual classifiers, so that they're uncorrelated. And if we can do that, then we can get a new bagged classifier that has a lower MSE. and it does better in general. And so the idea is to, one, choose a method with a low bias but high variance. 2, reduce variance through bagging. So the idea with bagging is bagging cannot help bias. The bias is whatever it is. So if we want the bias to be small, we need to choose our base method, the FBs, the F little b's, right? We need to choose that base method to be really low bias. Luckily, something that's low bias tends to have a high variance. And we can tamp down, we can control that variance by bagging things together, by basically averaging our models. And we can reduce that variance through bagging. So we'll choose a method that has a small bias. This part is small. Now, the variance might be high, but we can just average together a whole bunch of these and reduce that variance. And so then we are going to end up with a method with not only a low bias, but also a low variance. And we basically cheated. We've gotten our cake and eaten it too, because we have cheated the bias variance trade-off by averaging things together. We get both low bias and low variance. So we need a method that has a low bias but eventually high variance, and then we're going to bag it together in a clever way to reduce that variance. What method do we know that has that? Well, we go back up to the beginning of the lecture. Our problem, with another star here, with carts is that they tend to have a high variance, but compensating for that, they have a very low bias. So the idea is let's bag together a bunch of carts, a bunch of trees. They're really low bias because you can fit really complicated, really overfit complicated structures, relationships, but they tend to have really high variance. But we don't care about the high variance. We're just going to bag them together. We're going to average them together and get a better method. Enter the random forest. Which is basically a bagged cart. So random forests are basically averages, or in the case of classification, majority vote of collections of trees. And collections of trees are called forests. Hence we have a random forest. So typically this is denoted RF for random forest. And I'll write down the random forest algorithm. It's a little bit more than the bagging algorithm, but it's basically a bagging thing. What we're going to do is we're going to fit B trees. And in kind of the classic bagging setup, we're going to have some index little b, and we're going to have capital B of these. For each of the little b trees, we're going to first draw a subsample from the training data. And the classic bagging algorithm would be to fit a tree, say a regression tree or a classification tree, to each of these subsamples. There's a second random step in the random forest, is we're going to grow a cart, either a regression or a classification tree, on the subsample. That is, we're going to fit either a classification or regression tree to the subsample. But each time I split, I use or I consider a random subset of covariates to split on. So this is why it's called random, because normally for a classification tree or regression tree, at each split I can consider all possible variables. But a random forest is not going to allow us to consider all possible variables each split. It's going to randomly choose a selection of variables and say, okay, only choose those. And so it's going to build a random cart. So it's basically bagged random carts. And so we're going to fit the trees. Each tree is going to fit on a random subsample, and we're going to fit them with this little randomization step added. And then basically we're going to bag them together for prediction. So for a regression problem, we're going to average the answer, and for a classification problem, we'll take the majority vote. That's the whole, once you talk about bagging, that's the whole random forest algorithm. And so the idea, why this is a good idea, is that these two steps, and particularly the second step here, helps make the correlation between my individual trees, my individual f-hats, my f-hat b's, that row 0. And therefore, we're going to get this reduction in variance here that we want. So by randomly not only taking a subsample, but by adding this randomization step in, it helps a phrase here is it decorrelates the trees. And so it helps them be uncorrelated with each other. And that doesn't hurt the bias. The bias is unchanged, but it helps decorrelate it and so help drive that variance down. So as we saw in our little bit of math, the bagging trees in this way cannot hurt. It will never reduce or increase the MSE, kind of in a theoretical way, because your bias is always unchanged and it can reduce your variance. For a classification problem, we'll just briefly say it's a little more complicated. Bagging good trees helps. Bagging bad trees can potentially hurt. In practice, you have to have a really bad base classifier or really bad classification trees bagged together to actually hurt. In practice, it almost never hurts. But for regression, kind of mathematically bagging together things can't hurt. But for classification, theoretically there are situations where it could end up hurting. If you had a really bad set of base methods, base trees that bag together a bunch of classification, really bad classification trees, you could actually theoretically do worse. For regression, pretty much you can't hurt yourself by bagging. So it's almost always, you can hurt interpretation. It's harder to interpret these things, but so random forests are harder to interpret than just a regression tree, but it's not going to hurt you. For classification, that might not be true. You can come up with some weird situations where you might be hurt, but it generally happens when you have a really bad underlying base learners, as they're called. So the little f sub b's are often called base learners. Okay, in the last 5 minutes here, so that's the really dead simple. And once you know trees, random forest is dead simple. Explain why it works a little bit. It's really nice. Random forests are probably one of the best out of the box. Don't need a lot of fiddling with methods out there. So they're almost always one of the first things I go to, because you basically can't hurt yourself by using them. They tend to have both low bias and low variance, and they don't require a lot of fiddling around with. So we'll see that in lab. Probably one of the best, just straight up first things to go to when trying to solve a problem. Okay, the last thing I want to talk about is out of bag error, which is often called OOB. This is a really nice feature of random forests. So when I fit a random forest, it trains a collection of FB hats on subsamples. And so one way of thinking about this is that for any FB hat, there are some points very likely not used to train it. So because I take a random subsample when I fit each of these base learners, these F's and B's, there is very likely some data that I have actually my training data that doesn't make it into the random sample into the FB. Alternatively, the flip side of this is that for any training point, man, that handwriting's going, for any particular training point, let's just generically call it XY, there are some FB that don't use it. And generally there are a lot of these FBs, or like a third of the FBs aren't actually going to use it. So an idea is if for some XY, I bag only the FBs, or the FB hats, I guess they have hats on them, that don't use XY to train them, then my training point XY is basically a test point as far as this new bagged method goes. So the idea is that for any individual training point, there's going to be some collection of these F's and B's that don't actually use it in their training. And so as far as that collection of FBs is, this little training point, XY, is a test point. And so what I can do is predict error. We can basically predict a testing error for this particular training point, XY, using what is called the out of bag, or the OOB, by bagging together these the FBs that don't use XY, by using out of bag classifiers, or out of bag methods. It's a little bit cumbersome to write down, but it's actually a pretty simple idea. So for any individual training point, XY, there's some of these methods, classifier regression, that don't use it in their training. So as far as those concerned, it's a test point. So if I bag those together on the side and I predict on this point, and I see is it correct or not, that's basically an estimate of, it's basically a testing estimate. So my out-of-bag error, so random forest, basically, you don't even need to do a kind of cross-validation, because for each point I can do this. And so for each point, I can look at, just predict using the base learners that don't use my point, and I can do this for each point and calculate testing error this way. So basically, for each training point, I'm going to predict it by bagging together things that don't use it in their training. And then I'm going to have a bunch of predictions and a bunch of, and the truth, and I can calculate my error rate, whatever it is, and that gives me an estimate of my training error. My testing error. And this is called the out-of-bag error estimate. And so you don't really need to do this kind of cross-validation for this basic level of for random forest, because they kind of on the way, you can just get for free what's called the out-of-bag error, where you're basically predicting using subset, for each point using a subset of those base learners that don't use that point as a training, and therefore that's effectively an estimate of the testing error rate. And that's all you want to get out of a cross-validation, for example, or a test train split. So that's a real quick overview of random forests. We'll see in the lab, they're really just nice and powerful methods. Can be a little computationally intensive, but that's our first kind of ensemble method, which is bagging, and the most preeminent example of kind of bagging or an averaging, kind of model averaging, is the random forest.